Question number 8, that is acid and base. Now concentrated hydrochloric acid with concentration of 10 mole per decimeter cube is diluted. Now we're diluting to form 500 centimeter cube of a 0.25 mole decimeter cube solution. Is the dilute hydrochloric acid a strong or weak acid? Whether we dilute it or not, the HCl, hydrochloric acid, which is HCl, will always be a strong acid. So the answer is strong. Calculate the volume in centimeter cube of the concentrated hydrochloric acid that must be used. Now, once I say in centimeter cube, what are we having? A dilute. So once we are diluting these two, so we can use a formula, a dilution formula of say the number of moles before, or even if when we dilute, we'll have a container here and then another container here. Then if this is an acid, this will be a base. Now when you take this container, then the number of moles of the acid come rolling, it will remain the same. The number of acid will remain the same, the number of molecules, and even the number of the base will remain the same. Then when we make the dilution, so running, when you have this part, the acid before and the acid after will be the same. So whether we have that or not, so the dilution formula says the concentration can have a base, but let's have the information, let's collect the information. So initially, concentrated hydrochloric acid, so we have HCl with a concentration of an acid here is diluted to form a 500 centimeter cube. Now because this decimeter cube we cannot mix with centimeter cube, so it will be 0.5. So this is diluted to form of a solution, right? This is the volume. This is also the volume, but now when you have here, this is the volume after. This is the volume of course remain of acid after. And then this is what we're saying. The number of moles of acid before equals to the number of moles of acid after it is diluted. Before it's diluted, because we are mixing in one container, then it means that the number of molecules will remain the same before and after, but of course the volume will change, right? That will be the volume of the acid after, but the volume of the acid before, the volume of the acid before we don't have, but after we have this one of a volume, a concentration of acid after this. Then now we keep on this one. So you know that the concentration of the acid multiplied by the volume of the acid is giving us this. Even the number of moles after concentration of acid, the volume of the acid. Now that's why we have a dilution formula of the volume of the acid, concentration multiplied by the volume of acid. This is concentrated. You can put in brackets and say concentrated equals to the concentration of the acid multiplied by the volume of the acid, but this side is after. Now is dilute. Right. Now the information at dilute, we have 0.5 and then we have the concentration of 0.25. So we're going to fill it here. But for concentrated, we only have the concentration. So let's fill in the formula. The concentration of the acid concentrated 10 multiplied by the volume of the acid that is more concentrated equals to the concentration 0.25 of the acid that is dilute multiplied by the volume of 0.5 of that when is dilute. Now we're going to say the volume of the acid concentrated equals to 0.25 multiplied by 0.5 over 10. So the volume of the acid that is concentrated. So we are going to have, let's bring the calculator. So it's 0.25 multiplied by 0.5 divided by 10. So this is 0.0125 but this is in decimeter cube. So therefore the volume in of the acid in decimeter cube. So we're going to take this, now we multiply by answer multiply by 1000, so we'll have 12.5 centimeter cube. Now that will be the answer here. Next, calculate the pH of the concentration of 0.25 moles of HCl. Now the pH formula says pH equals to minus the log of the concentration of the hydronium ions, like this. So this is equals to minus the log of, now they said concentration of this one. So because it's a monoprotic, so not, it means the concentration of HCl is the same as the concentration of the hydronium ions. So because it's of monoprotic, is 1:1. So now it means now we're going to have the concentration of 0.25 here. So when you press calculator, let's press that on the calculator. So we're going to have negative log of 0.25 Now we have 0.60. Now that will be the pH of HCl. 0.60, so it's too strong or too acidic because the pH is more less than, even less than 1. Right, long question. Calcium carbonate forms a large percentage of sea shells. That is calcium carbonate is here. In order to determine the percentage purity of the calcium carbonate in seashells, learner react 5 grams of powdered seashell with 500 centimeter cube of dilute hydrochloric acid, prepared in question 8.1. Now we'll use the information in 8.1. We had a dilute acid to be to have the concentration of the dilute acid was 0.25 mole per decimeter cube. And then this of dilute, and then we had a volume of the acid of dilute to be 0.5 mole per decimeter cube. That was the information of in 8.1. All right. Now they're saying we're taking 5 gram powdered seashells with the 500 centimeter cube of the dilute. Yes, that's what we're saying. Dilute hydrochloric acid prepared in 8.1 with the concentration of this. The reaction takes place in is represented by the following balanced equation. So this is the one with we're reacting with HCl. Now this will be the products. Now they're saying the excess HCl is then titrated with 140 centimeter cube of 0.2 mole decimeter cube solution of sodium hydroxide. Now we have another reaction here that is kind of hidden. So let's see. It means we're going to react this, we're going to have this reaction. Now they're saying this will be in excess. In excess meaning prior to shine, or this one will react completely. Meaning running this one into a fella. So it's no fella or shala HCl. Namila HCl or shall ishijigan. Now by reactor, that is why they say the excess is then titrated with 140 centimeter cube of 0.2 mole decimeter cube of the sodium hydroxide. So now it means we have NaOH now reacting with HCl, that was excess, and then of course this will produce the sodium chloride plus, of course, looking at this one, we'll have H2O here. Right, this is what we're going to have if we're titrating this acid with the strong base. Right, now the information is here of sodium hydroxide. So we're having a volume here of how much? Of 0.14 decimeter cube. Let's check. We say 140. 140 divided by 1000. So of course it's 0.14. And then they also said it's saving a concentration of 0.2 mole per decimeter cube. Right, sorry for that. Right, now we have the information of NaOH that is titrating the excess HCl. Right, it's fine. Let's get the question. Calculate the mass of the calcium carbonate present in the sample of seashells. So we're looking for the calcium, the mass of the calcium carbonate. Where is it? It's here in the beginning. All right, let's check something here. This HCl was in excess. So HH. Then right here I rectified directly NaOH. And this NOH, look at this, they produce H2O. So it means what is left in the system of this titration. So it's kind of we are having it's kind of we're having a neutral solution here. So what this is the case. So here, that's when things are reacting. So we take the excess one. So this will be the initial, and then from there this will be the kind of final. So we're going to have our number of moles initially, and then we'll have the one for final. So taking this in account, so we'll check how much of HCl initially create the number of moles, so that finally then initial finally then what is the amount that is reacted or short. So e shortang gore ke reactileng le these two reactions. Then I reacted these two, then it means we're going to have the reacted calcium carbonate. So now I get this one and NOH, one is say titrated. So once it's titrated, it means here that's why we have strong acid and a strong base and strong acid, so they'll produce neutral, meaning neutral all of them they've been reacted completely, so because they produce the neutral. So running we'll get what was in the final, that was reacted in. So it's fine. Let's get running the one that is excess the reacted part of what was the base. That's why we'll get the mass of with that. So where do we start? It's fine. We can start from the initial. Do we have the number of moles of HCl initially? The number of moles of HCl, that is the initial part. Do we have that before it comes initial already? Before it will in excess already erectile before it was shallow. So available guy. So before it was shallow, so the number of moles here. Renaling parfile on reaction one that is prepared. So we're going to have concentration of acid multiplied by the volume of the acid. So available guy 0.25 multiplied by 0.5. So using your calculator, you get 0.125 moles. That is what that is initially when before it reacts with the sodium, the calcium carbonate by preparing initially veiling. Then it's fine. Finally, it reacted NOH, and then this NOH it reacted completely. So we're going to use the number of moles of NOH. We'll refer what was the number of moles that is reacted with this NaOH. So we can call it final, because finally we share the excess reactant, this one. So we're going to have the number of moles of HCl equals to the concentration of the acid HCl multiplied by the volume of the HCl. Here it is, calculate the concentration of the, sorry, for this one should be for the base. For the base, why base? Because for HCl arna sale, it was in excess by GI rectal NaOH. So, but because NaOH rectile kamoka, arbonore, irritiate how much amount of the acid, irritiate how many number of moles of the acid. So that's why we need to get the number of moles of NaOH restoring K kanga irritiate HCl. So NaOH here. So we're given the concentration is 0,2, and then we're given the volume is 0,14. So when you get that, multiply, we get 0,028 moles. Namile ke reactile completely with the excess HCl. So what is the ratio of that? So the number of moles of NaOH is to the number of moles of HCl that was in excess, and then now the ratio is 1:1. So when you do the cross multiply, this will multiply this one, and this one will multiply this one. So it means it's 1:1. So we're going to have the number of moles of HCl is the same as the number of moles of NaOH. So giving us 0,028 moles. So this is the number of moles, the final of the HCl initially was this one. So let's check, or originally this one, then now if we finally fedijele this one. So if it this one now, let's check what amount reached because the whole of this reacted with NaOH, but how much of them was reacted with this calcium carbonate? Then we're going to get the number of moles of HCl reacted roaring reacted roaring only initial, and then wabale a final. So meaning we'll take the one that was initial, the number of moles of HCl initial minus the number of moles of HCl final. So let's substitute. The number of moles initially was 0,125 minus finally Ferrigel 0,028 moles. So when you subtract the two, the number of moles reacted of HCl already reactile with the calcium carbonate. So it's giving us 0,097 moles. So if that is the case, so this 0,079 moles, so we need to get, because this is the reacted of HCl that is reacted with this one, so we're going to use the ratio to get how many number of moles of acid that is reacted with the calcium carbonate, because it shows that the number of moles totally reacted is this one, 0,097. Let's clear this one here. Right, Right. Now we're going to say, okay, the number of moles of calcium carbonate with the ratio of the number of moles of HCl reacted, that will be 1:2. So meaning when you do the cross multiplication, so we're going to have 2 times the number of moles of calcium carbonate equals to 1 multiplied by the number of moles of HCl. Now we need the number of moles of calcium carbonate, so we divide both by 2, so it means it will be half. So now it means the number of moles of calcium carbonate equals to 1/2 of the number of moles of HCl reacted. Now, of course, the number of moles of calcium carbonate equals to half of 0,097. So that should be 0,0485 moles. Now we have the number of moles of calcium carbonate that is reacted. Now, if we have that, now we can get what? We can get the mass equals to number of moles multiplied by the molar mass. So the number of moles is 0,0485 multiplied by what is the molar mass? Now the molar mass of calcium carbonate is 100, and then that will be a mass of 4,85 grams. So that will be the mass of the calcium carbonate that is present in the, I would say that is the one that is reacted in the sample of seashells. That is the one that is reacted. Maybe that is the one that is present. Oh, of course, that is the one that is present because it means all of it was reacted. Why? Because the HCl was in excess. HCl is huge, so HCl roaring is or irregularly the calcium carbonate come down. So roaring that is one that was present, all of it. Now the last question is, calculate the percentage purity of the calcium carbonate in the seashells. The percentage purity here, the seashells. Now so okay, so it means we are given the mass of 5 grams here. That is what's the total mass. So but at the end we managed to get this other one reacted. So it means if the total was 5, so it means they were impure substances that covering the calcium carbonate there. So what do you do with that? Let's put it up here. So we are going to have the percentage purity equals to the mass of calcium carbonate, which is the mass of a pure substance, and this is the mass of impure in other words, which is a sample. So a sample was 5 grams that is containing the impure substances. So we'll have 4,85 over 5. But because it's a percentage, you multiply by 100. Even here, multiply by 100. So we'll get an answer of 97%. So that will be the percentage purity of the calcium carbonate that was found in the seashells. So we're done with this question. Hey, long question of acid and base. So I was concentrated with lots of calculations.